Let's examine first some properties of tangents. Tangent property number one, intersecting tangent and radius are perpendicular. So you see in this picture, this right here, this line is a tangent because it is only touching here, that at the point of tangency, and here is a radius. When a tangent intersects with a radius, they will intersect at a right angle. They will be perpendicular. You'll notice in this animation that no matter where I put that point of tangency, I can drag it anywhere in the circle. If it intersects the radius, that tangent is always making a 90-degree angle with the radius. So again, tangent, radius, perpendicular. They're going to make 90 degrees. Examples. Determine if segment AB is tangent to circle C. Number one, if this segment AB is going to be tangent to the circle, then remember, according to the tangent property, the tangent and the radius must be perpendicular, therefore make a 90-degree angle. So I'm trying to test to see if this and the radius are making a 90-degree angle. I'm going to put a question mark there because I don't know that right now. How would we figure out if it is a 90-degree angle? Well, notice that this segment and this radius and this segment make a triangle. If this is a 90-degree angle, it would make a right triangle. And remember, to test if something is a right triangle, we would use the Pythagorean converse. C squared blank a squared plus b squared. We're trying to see, is it equal? Well, the C is the side across from the possible right angle. That would be the possible hypotenuse. How long is that? Well, this part says 2, but notice the 2 is in the middle of this little segment, which means it's only for this piece right here. Also, if that's the right angle, this would have to be the longest side, and 2 is not the largest number between the 3, the 4, and the 2. If the 2 is out here, that means we need to also have this length. Well, if this radius is 3, it means this is also 3 right here. So altogether, this length is 5. So C is 5. 5 squared, and then A and B, 3 and 4. 3 squared plus 4 squared. Now, we could know right away that this is going to work because of the triple 3, 4, 5. We know that makes a right triangle, but let's just verify. 5 squared is 25, 3 squared is 9, and 4 squared is 16, and 9 plus 16 is 25. 25 equals 25. Therefore, yes, this is a right angle, which means yes, AB is tangent to circle C. Let's write that as our final answer. AB, the segment AB, is tangent to circle C. In number 2, notice how this one is labeled. The 10 is in the middle of this entire segment. Is AB tangent to this circle? Again, if it were tangent, we would know that there's a right angle here. I'm going to put a question mark because I don't know if there is yet. Because the 10 is in the middle of this segment, I know 10 is that entire length, so I can use 10 for the C. 3, 9, and 10, 10 is the longest. So 10 squared blank, 3 squared plus 9 squared. 10 squared is 100, 3 squared is 9, 9 squared is 81, and 9 plus 81 is 90. 100 does not equal 90. So in this case, that is not a right angle, and therefore segment AB is not tangent to circle C. Let's look at the third example. Given the tangent segment intersecting with the radius and the secant segment shown below, find the radius of the circle. Find the radius. So they told us it's a tangent. And remember, tangent is perpendicular to radius. So if this is a tangent, then it has to make a right angle with the radius. Has to. Well, this 6 right here is labeling just this section from here to here. Notice how the 6 is in the middle of that segment. It's not in the middle of the long segment, so this is also a radius r. If we know that this is a right triangle, to find a missing length of one of the sides, we use the Pythagorean theorem. C squared equals a squared plus b squared. Now this is going to be a little tricky because we're not missing just an entire side, we're missing a piece of a side. So let's see how we can do this. Across from the right angle is the hypotenuse. This whole side is the C, the hypotenuse. Part of it's 6, part of it's r. How do we put those together? Add them. 6 plus r. So in the C, we're going to put 6 plus r. All of that will be squared. Then we can fill in the other two sides adjacent to the right angle, r squared and 9 squared. How do we square this? We write it twice because that's what square means, multiply something to itself, and then we FOIL it. Let's not forget there's a right side of the equation, so I'm going to write the rest. What does that mean to FOIL? Well, basically distribute. 6 times 6 is 36. 6 times r is 6r. R gets distributed. R times 6 is 6r, and r times r is r squared. And then we'll write the rest of the equation. Now we can combine like terms. Here's an r squared, subtract it because it's added, and do it on both sides. Luckily, it goes to 0 on both sides. No more r squareds. We can combine these like terms to 12r. So I have 36 plus 12r equals 81. Here's the r. I want it by itself, so minus 36 from both sides. Left over with 12r equals 45. Divide by 12. R equals 3.75. Exactly. Let's look at another property of tangents. Property number 2. Intersecting tangent segments are congruent. Let's take a look at this picture. It will be given that segment RS and segment RT make right angles with the radii of circle C. See, here's a right angle, here's a right angle. Well, if they make right angles, that means this has to be tangent because it's perpendicular to the radius, and this has to be tangent. So these are two tangents. Notice they intersect outside the circle at point R. What else can we determine? Well, if S goes to C and T goes to C, those two little segments are both radii. So since radii of the same circle are all congruent, we can put little congruent slashes there. SC is congruent to TC because they are radii of the same circle. What else? Well, notice we have a triangle on the top and a triangle on the bottom, and both triangles share this segment RC. So we can say it's congruent to itself. RC is congruent to RC. Do you remember what property tells us that? It's a shared side, but we say the reflexive property tells us that a segment is congruent to itself. So notice what we have here. A triangle with two congruent sides and an angle, a right angle, congruent to a triangle, two sides, and the right angle. So these triangles are congruent. Triangle RSC is congruent to triangle RTC by the hypotenuse leg congruence theorem. Why do we care? Well, because then it tells us that any corresponding parts have to be congruent, such as this remaining side and this remaining side. So therefore we can say RS is congruent to RT by corresponding parts of congruent triangles being congruent. Well, remember, we said these two are tangent, so these tangents have to be congruent. Just a little reason why that's true. Let's take a look at an example of how to use the fact that intersecting tangent segments are congruent. So first of all, we identify in the picture that we have a tangent segment and a tangent segment. So this side is congruent to this side. How do we show that? Make them equal. And then we solve. And there we go. Tangent segments are congruent.